Hello, everybody. So now we are going to try to answer the question that we were asked last time, which is how uh, or why did we choose the hypothetical path to be in this shape, and we will see how to calculate the enthalpies of each one of these segments that we have here in order to calculate this delta H and get the total enthalpy difference between state 1 and state 2. And to answer this question, we will start with one piece of information, which is what are the conditions under which we can calculate the enthalpy difference. And there is one point that needs to be clear before we answer this question, which is what are the factors that affect the enthalpy. So the enthalpy is affected by pressure, temperature, and phase. If there is any one of these conditions changing, the enthalpy will change. Of course, this is for pure component. So we're not talking about mixture. If it's a mixture, then we will have the composition as another factor. But for pure components, one of these three must be at least one of these three will affect the enthalpy. Either if there is change in pressure, if there is change in temperature, and if there is change in phase. So the conditions that we can do the calculations for enthalpy in is when we keep two constant and change one or the third parameter. So for example, for the first case, we can calculate the enthalpy when there is a change in pressure at constant temperature and phase. The second condition is when temperature is constant and the phase and pressure are temperature is variable and pressure and phase are constant. The third is when there is phase change while pressure and temperature are constant. So these are the main three cases that we can do the calculations in. There is one extra case which is related to mixing more than one component. If we have mixing of two liquids, or dissolving gas and liquid, or there is mixing more than one component, which we call the heat of mixing, which is one other parameter that affects the enthalpy. There is another case when there is a chemical reaction. So the first three or the first four are for physical systems where there is no chemical reaction involved. If there is a chemical reaction, then the reaction, because the reactions might be endothermic, might be exothermic, they might produce heat or absorb heat. So this will change the enthalpy of the system. So in this case, we can consider this as one more case. What we're going to cover here in this, so before we proceed, if we look at these cases and you check back the hypothetical path that we put here, you'll understand why we put all these segments here. Each one of these segments include change in one of the three conditions. Here you have change in temperature, here there is a change in phase, here a change in temperature, change in phase, change in temperature, change in pressure. I couldn't combine more than one because this is what we can calculate. So I have to break the delta H into small segments. Each one of them is one of these cases that we have here. Either changing pressure at constant temperature and phase, constant pressure and phase and changing temperature, phase change, or whatever. So these are the cases that I can deal with. And this is what I should keep in mind when I am putting the hypothetical path, because you need to make sure that the hypothetical path that you put is something that you can calculate. It's not something that is just a path. It's a possible path, but it's not something that you can calculate. And now I just want to discuss quickly what we are going to cover in this course regarding these cases, and which part is in chapter 8 and which is in chapter 9. So the first four cases are in chapter 8, which are all the physical systems. And if you remember, in the cover slide here, we said this is balances on non-reactive processes. Non-reactive processes, which are processes that do not include any chemical reaction, which is changing in conditions or mixing of more than one component. Chapter 9 is going to be concerned with the reactions. If there is a reaction, we will see how we can do the calculations for a system that includes a chemical reaction. What we are going to cover in this chapter is parts 1, 2, and 3. Part 4 is not going to be included. It's not part of the syllabus, so I am not going to cover this. It's in the textbook anyway, so you can check it if you are interested. But what I'm going to cover in this course is, or in these videos, is the first 3 cases, and inshallah in chapter 8 chapter 9 we are going to cover condition number 5, or part number 5. So again, our abilities to do the enthalpy calculations must be very clear, because this is what we are going to be depending on when we put the hypothetical path. Before we proceed, there is one quick thing that I want to mention, which should be a very known thing, which is the definition of ideal gas, because we will see later cases where we are talking about ideal gases or non-ideal gas. So an ideal gas, this is very briefly, just to give you an idea of what we mean by an ideal gas. So an ideal gas is a gas that satisfies the following conditions, or has the following properties. First, the molecules are very far from each other, so there is no interaction between them. So you have very large space and a small number of molecules, so the molecules are going randomly in space without seeing each other. So there is no chance, or very little chance, of a molecule to collide with another or to hit another molecule. The volume of the gas mixture or the gas molecules themselves is very small compared to the space that they are occupying. For example, if you have 1 meter cube, you will have, let's say, 100 milliliters of the volume is the actual volume of the gas, and the rest is the space between the molecules. So this is 10 power minus 4 of the volume. I'm just giving this as an example of the number, but this is the point, that the molecules are very far from each other, so they are occupying very small space, because the majority of space is not occupied by anything, or what is called the spaces between the molecules. So the ideal gas is described using the ideal gas law, which is PV equals nRT, and this is a known thing. And the volume here is used to describe the intermolecular spaces, which is the space between molecules, or the space that is not occupied by the molecules. So again, if I have 1 meter cube, then of total volume, and the gas molecules are occupying 100 milliliters, which is 10 power minus 4. So 1 meter cube minus 10 power minus 4 is going to be the volume that we should substitute here. And since the volume of the gas is very small, we can ignore it, and we assume that the total volume of the container is the volume of the intermolecular spaces that we substitute with here. So this is what we mean by ideal gas. The other type of gases is what we call the non-ideal gases, or sometimes called real gases. The non-ideal gases are gases that are not ideal, which means that there is a very big chance of the molecules to collide. The intermolecular spaces are very small, so that's why we call it non-ideal gas. This non-ideality can be a result of more than one reason. It can be due to having very high pressure. So the high pressure makes the molecules more stacked or more packed in the place or in the container. So this makes it behave in a non-ideal way. Or the nature of molecules. Sometimes molecules are non-ideal. For example, the water molecules, there is a natural interaction between the molecules. They naturally form hydrogen bonds. This hydrogen bond is a form of interaction between the molecules that makes the water vapor molecules behave in a non-ideal way. So this is one other thing that would make the molecules non-ideal. Anyways, there are a lot of details about the ideal and non-ideal gases, but this is the main idea that I want to, or the main points that I want to make clear before we proceed, just to understand what we mean by ideal gas and non-ideal gas. And there are regarding the non-ideal gas, there are many equations. Thermodynamics is stacked with equations that are derived, and they are done to express the behavior of non-ideal gases. But we're not going to go through this because this is the concern of thermodynamics, so it's not of our concern right now. So what we're going to discuss now is the how we can calculate the enthalpy change uh, due to the change in pressure at constant temperature and phase, which is the first case. This case is a very simple case because if you remember, we saw these two plots at the end of chapter 7, and these were data that we extracted from the steam table showing how the pressure affect the enthalpy and the internal energy, and how the temperature affects the pressure and the enthalpy and internal energy. And we said that the temperature at constant temperature, here the temperature is constant, and you can see the enthalpy is changing very small due to a large change in pressure, and the same for internal energy. On the other side, the enthalpy was very dependent on temperature, and this is something that must be clear, that the pressure effect is very minimal compared to the effect of temperature. So when we talk about the conditions or the calculation of change in enthalpy and internal energy due to change in pressure, we have cases for solids and liquids. And for solids and liquids, the experiments that were done proved that the internal energy, the specific volumes, and the enthalpy of the gases and solids and liquids are not affected by or the internal energy and specific volume are not affected by the pressure. And this is an expected thing. We know that liquids and solids are incompressible. So if they are incompressible, it means that the volume is not affected by pressure. No matter how high the pressure you apply, the effect of the specific volume or the volume is going to be very small, if there is any change at all. So the specific volume is not affected, and the internal energy is found experimentally to be not affected. So according to the equations that we have, which is the relation between the enthalpy and internal energy, then we will have this delta H equals delta U, which is 0, plus delta PV, which is V hat delta P. It should be V hat delta P plus P delta V hat, but delta V hat is going to be 0 as well. So it's going to be only V hat delta P. So this is for the effect of pressure. There is no effect on internal energy for solids and liquids. The only effect is for the enthalpy, which is V hat delta P. And by the way, this is usually not a very big number. So this is the first thing. The second thing, which is the conditions of gases. For gases, we have two options. Either the gas is ideal or non-ideal. For ideal gases, enthalpy and internal energy are not affected by pressure. There is no effect of pressure on the ideal gases, and we assume that delta H and delta U are almost 0 if there is an isothermal pressure change. When we say isothermal pressure change, we mean that it's the pressure change at constant temperature. This is the meaning of the word isothermal. Unless the temperature is very low, then we can do some calculations to calculate delta H and delta U, or if the pressure is very high, if we have like 60-70 bars, in this case we need to find out how this will, because in this case it's not going to be ideal gas. So this is something that we can expect. For non-ideal gases, then this is going to be a very complicated thing, either to go for steam tables if we have steam, or we can find for some correlations from thermodynamics that we can use. But again, this is something that's going to be out of scope of this course. This is going to be a very thermodynamic thing, so we are not going to be interested in this. So just to make it easy for us, the cases that we can deal with are the cases for solids and liquids. And these are what we can do for solids and liquids. Of course, this is due to the change in pressure at constant temperature and phase. And we can know how delta H and delta U are calculated, or that they are zero in case of ideal gases. Real gases are a different topic that we cannot cover here. Uh, One last thing about the V hat, this V hat, which is the specific volume. The V hat is the specific volume that we can get by one of two things, and one of two methods. Either for liquids, we can calculate it from the specific gravity. So we know V hat is 1 over density, and the density is specific gravity multiplied by the reference density. And of course, we know the reference density is the density of liquid water at 4 degrees Celsius, which is going to be 1000 kilograms per meter cube. So this is one option, and in this case, this is going to be in meter cubes per kilogram. If you want to make it a molar volume, then we can use the molecular weight, so we can multiply it by molecular weight, so it is kilogram per kilomole, so it's going to be meter cubes per kilomole instead of meter cubes per kilogram. So this is how we can get it. We have another option if you have tabulated data, like in case of steam. It's not always available, so we are more interested here in the liquids. For the solids, you can find the density of solids easily from tables or from whatever the source that you can find it in. But I'm just mentioning this here because this is something we have in the textbook, which is the table of the physical properties, which is table B1. This is, and now we will see that we are going through the tables. We are going to use a lot of data from the tables in the appendix. We discussed the steam tables, but now we are discussing the rest of the tables. So here we have, for each one of these molecules that or compounds that we have here, you have the molecular weight and you have the specific gravity. So this is the specific gravity that we use to calculate the specific volume, which is the third or fourth column in the table. We're going to go through all the rest of the columns later, but for now, this is what we are interested in now, inshallah. So this is all for this video, and there is not a lot of discussion about the pressure. So pressure is going to be just what we said. The temperature is going to be the main factor that affects the enthalpy, and this is what we're going to spend a lot of time talking about. So we'll start this next time, inshallah. So I'll see you then.